Welcome to Module 1 of Biostatistics HNAS 699, Why We Use Statistics. This first mini-lecture will be a little bit more detailed than the other mini-lectures that will accompany the other modules. For some of the other modules, I might post a summary of the learning objectives and then just go into one or maybe up to a few different topics as separate mini-lectures. But because this is the first one and it's an introduction of why we use statistics, it will be a little bit longer and a little bit more detailed. So the summary of the learning objectives for this module is that you should be able to describe the differences between descriptive and inferential statistics, define relevant terms for statistical approaches and experimental design, distinguish between qualitative and quantitative variables, and this will include distinguishing among nominal, ordinal, interval, and ratio scale data, and then composing an experimental plan for the analysis of data. So in general, the question could be well, why would we want to use statistics at all? And that's because inherently there is variability in any biological system that you would be interested in, including in the health professions. And that variability is a fundamental source then of our uncertainty when we want to have an understanding of data. And the use of statistics is actually common across many fields to try and synthesize down the information that we get from data in order to get a clear message. And there are two main types of statistics. So when you hear the word statistics, you might think, well, what do people mean? It could be either descriptive statistics, which you should be familiar with already. So this includes items such as the arithmetic mean, the median, and the mode. And it's a way to summarize or describe a set of data, and there'll be a whole module related to this later on as well. And then there are inferential statistics, where we use information on measurements from samples to infer something about an actual population. And a lot of this course will be related to descriptive and inferential statistics. So statistics in the research process. So where does statistics play a role? Well, the first step, of course, in the study is to come up with a hypothesis. So this is a conception about the issue or question that's being studied that can be based on the results of previous studies or direct observation. And then the hypothesis would lead to one or more predictions that could be studied that would be unique to this hypothesis that are testable. In the second step, you come up with a study design. So how could you actually collect data that would be used to test the unique predictions from the hypothesis? And it could be designed as a observational study where it's just looking at how things are naturally. However, it's often difficult in these situations to differentiate cause from effect. Or it can be experimental, where there's a manipulation that's done for at least some subjects, and sometimes manipulations can introduce some unintended influences, so one needs to be careful when doing an experiment. Data collection doesn't involve really statistical considerations, but it does require careful attention and consistency in methodology and in data recording. Then we actually get into the statistics part of it. So once you have the data collected, you can look at both the descriptive and inferential statistics. And often the types of analysis that can be used are limited by the decisions that are made during the study design. So that's important to keep in mind. And this will come back further on in the course as well. And then the fifth step, of course, is to take the analysis that's been done and relate that back to the hypothesis. And are the predictions supported, and is the hypothesis supported? If the hypothesis is not supported, then one must reevaluate their understanding of the system. But if the predictions are supported and the hypothesis supported, one important thing to note is that it doesn't mean that it has been proven to be true, because proof is not a scientific concept. And I say this because other processes that were not considered by the study could also be responsible for the phenomenon. And in your textbook, it includes the 3 steps of conducting analysis of a data set, and these really are reflected in steps 4 and 5 that I've shown here. And so why should health professionals care about statistics and having an understanding of statistics? It's important because decisions about treatment methods are derived both from research articles and from one's own research, and the ability to understand these statistical approaches and statistical results is critical, because faulty statistics can actually lead to harm, and despite the fact that it is believed that statistics are important across a number of different disciplines and in the health profession, often incorrect statistical analyses and interpretations do occur. So we're trying to avoid that by making sure that you have a basis in biostatistics in this course. There are a number of definitions included in this module in your textbook. I'm not going to go into details here with these. You can refer to the text. But one tip is to remember that parameters are for a population and that statistics are used to describe samples. And this will come back. We'll talk about this more again later on as well. Also, we talk about the types of variables to measure. So variables are characteristics that can take on different possible outcomes, and quantitative variables are levels that indicate different amounts, and qualitative variables are categorical and descriptive. So values do not indicate different amounts of a level, but could influence a relative order. For example, being a sophomore versus a junior or something like that. I'm going to take a little bit of time to talk about these scales of measurement for variables, because sometimes this can be a little bit confusing. So a nominal variable is something that's categorical. It's referred to as classification or an attribute variables. So some examples for this could be color or sex, race, or the presence or absence of a trait. And in these cases, the outcomes can vary qualitatively and fall into mutually exclusive categories, right? So if you're looking at color and you have a series of different colors, it can only be one or the other. Or if it's examining the presence or absence of a trait, it's either there or it's not. And no specific arrangement of categories is actually meaningful. So, for instance, again, with the color example, you can arrange those in any order that you want. It doesn't actually, for nominal variables, it doesn't actually mean anything. So you cannot manipulate nominal variables mathematically, and even if numbers are assigned to these categories, they are arbitrary and do not have any real meaning. A second scale of measurement is ordinal, also known as ranking variables. And there's one particular arrangement of the categories that is more meaningful than the other. So some examples here could be if one was interested in a gradient of color and went from dark to dim to bright to blinding, or if there was a dominance hierarchy or a preference ranking. Another example could be a headache pain ranking, going from no pain to slight headache pain to moderate headache pain and severe headache pain. With the headache pain example, a particular arrangement of these categories is much more meaningful than the other, right? Going from no pain to the most severe pain. And any other order would not be logical. Again, with ordinal classifications of variables, even though you could put numeric ranks on these, those numbers again have no quantitative information. So if you rank the levels of pain, it doesn't mean that, from 0 to 1, 2, and 3, it doesn't mean that 3 is one more unit above 2. So again, because ranks have no quantitative meaning in this case, you cannot do any meaningful arithmetical operations. So figuring out a mean, for example, wouldn't make a lot of sense. So this is sort of just what I covered here. The next one is interval scales, and these are quantitative or numerical variables, and there's a 0 point, and scale measurement are arbitrary, but the intervals between the numbers are equal. And a great example of this is temperature. It could be measured either as Celsius or Fahrenheit without any loss of information, right? Zeros are at different points for Celsius and Fahrenheit. And the degree increment measurements are consistent for both of them separately. And then the last one is ratio, which is quantitative and numerical, and there's actually a true 0 point, right? So if there was a weight of 0, then the weight is 0. Or for blood pressure, also there's a true 0 in that case. And all arithmetical operations are possible on ratio scaled variables. An additional point to note about different types of variables is that you can convert from one type of variable into another, but only in a particular order. So with ratio, we know that we have sort of these true values with a 0 meaning a real thing, and a value of 20 would be twice that of a value of 10. So you can go from ratio, convert that into interval data, convert that into ordinal data, and then convert that into nominal data, or that categorical data. So you can go in that direction, but if you start with nominal data, there's no possible way to go in the other direction to end up with a ratio scaled variable. There are also experimental design variables. These are described quite well in the textbook as well. Basically, the independent variable in designing an experiment is the treatment that's being applied. It's related to the cause of what you're trying to look at. And on any graph, it's typically the x-axis. The dependent variable is that response. So it's where you're examining the effect of that independent variable. And it would be a y-axis on graphs. So when we think of independent and dependent, the dependent variable is the response variable, and it's responding to the treatment, which is the independent variable. Something that always takes some consideration is thinking about extraneous variables. So these are other factors that could be influencing the response or the values of the dependent variable. And it can lead to a confounding effect. So when there's some other variable, this extraneous variable, that we're not really interested in looking at is actually causing the pattern that we see. So an example could be, for instance, that there's a nurse and they want to determine whether a new urinary catheter is less likely to result in urinary tract infections than a standard catheter. There's 40 patients who require long-term catheters who are selected for the study, and the new catheter is used on 20 patients who are predisposed to a UTI. The standard catheter in this study is used on 20 patients who are not predisposed to UTI. After 6 weeks, the nurse compares the percentage of patients using each of the two catheter types that develop a UTI. And the problem with this study is that it guarantees that the effect of the different catheter types is confounded with the effect of a predisposition to a UTI. So that predisposition to a UTI is a sort of extraneous variable that exists in this data that's going to influence the results. And no statistical analysis could fix this because it's completely confounded. So what could be done differently in this type of a study to actually deal with the extraneous variables? Well, only using individuals in one group could help. And by group, I mean, are they predisposed to a UTI or not? So perhaps taking the group who are predisposed to UTI, assigning half of those individuals to the new catheter and half to the standard catheter would then let you know that information for individuals who are predisposed to UTI. So those are a lot of the main points that are examined in Module 1. And the textbook should give you a lot of information, and I'm going to also record another short example looking at the different categories of variables, the nominal, ordinal, interval, and ratio scale variables.